Hello everyone. In this video, we'll be covering the second part of electromagnetic effects, which covers the Fleming's right-hand rule and the working principles of an AC generator. In the previous part, we covered the right-hand grip rule, the Fleming's left-hand rule, and how it applies to a DC motor. If you haven't checked that out, I suggest you do before you move on to this part, as you do require some knowledge from there that needs to be applied here. Anyway, let's move on. So continuing on with this, uh, the Fleming's left-hand rule, if you recall, requires you to place your thumb, index, and your middle finger perpendicular to each other, right? The same is true for the Fleming's right-hand rule. You have to do the same thing, but with your right hand. So you may be questioning now what is the point of the left and right hand rule? They're both the same thing. You're pointing your finger the same directions and having the same orientation. But the fact of the matter is, they're used in different situations. Okay, so the first situation was when a current carrying wire was placed in a magnetic field, a force was exerted on that wire, right? That was your first situation. So when a current carrying wire is placed in a magnetic field and a force is exerted on it, that's when you use the Fleming's left-hand rule. However, there's another scenario in which you cannot use the Fleming's left-hand rule, where you have to use the Fleming's right-hand rule. And in this scenario, the current is not initially there. Like a conducting wire is placed in a magnetic field, but there is no current. The wire does not carry a current. The current is induced. This phenomenon is called the electromagnetic induction. So this is when you use the Fleming's right-hand rule. If you haven't noted it down anywhere, I suggest you do, like everything that I just talked about, because it is very important and it's something that should always be in your mind, as errors in using the left-hand rule and right-hand rule are very common in IGCSE and even at A levels. So that is something you need to always remember. Okay, now we'll move on. So first of all, I'll explain the principles of the electromagnetic induction, which I technically outlined just a few minutes ago, but this is basically the orientation of the hand, okay, in which this represents the force exerted, not exerted, the force applied by the human, and this represents the magnetic field, and this represents the current direction, okay. And I like to remember this the same way: father, mother, child. Okay, so in this scenario, in a magnetic field, so north and south, a current carrying wire is not a current carrying wire, sorry, a conducting wire, something that can carry current, is placed. Okay, so there's a magnetic field from here to here, and in this case what you do is you, or the human, exerts the force on the wire. And when the human exerts the force on the wire, there is a change of magnetic flux, or well, the magnetic flux is basically the magnetic field lines. So there is a change in magnetic flux. In IGCSE level, you can refer to it as the magnetic field lines are being cut, right? So let's say these are the magnetic field lines. Okay, it goes from here to here to here. Okay, it doesn't get smaller, but yeah. So when you move the wire, let's say the wire is here. Okay, there's the wire. When you move the wire through this, okay, it cuts through the magnetic field lines. So this is when a current is induced. When you apply the force, a current is induced in the conducting wire. Okay, and this is when the Fleming's right-hand rule is used, and this is known as electromagnetic induction. The phenomenon of a current being induced in a conducting wire when there is a change in magnetic flux, i.e. a force is applied onto it to cause a change in magnetic flux. I hope that makes sense. So in this case, using the Fleming's right-hand rule, what would be the direction? Okay, wait, I haven't given you the direction of the force applied. Okay, the force applied is towards you, as in out of the plane. So what would be the direction of the current? So if you hold your hand right, the Fleming's right-hand rule, not the left hand, do not use the left hand here because you're applying the force, not a force is being exerted. So you point your index towards, from the left to right, yeah, and then the force is being exerted towards you, so the thumb should be pointing towards you. And if you have done this correctly, your middle finger, i.e. the direction of the current, should be pointing upwards. And because it points upwards, this is the direction of the conventional current. Okay, this is pointing upwards, so the direction of the conventional current is upwards. So the current induced is upwards. Okay, and this same principle you can use in an AC generator. So in an AC generator, unlike in DC motor where you're converting electromagnetic energy into kinetic energy, in an AC generator what you do is the opposite. You convert the kinetic energy into electromagnetic, or more often than not, electrical energy. So this is a proper diagram of an AC generator, like a basic diagram, a very, very rough diagram. And this is what's used to rotate the coil. So when you rotate the coil, you can see that it's cutting, like there's field lines here, right? So it's cutting through the magnetic field, i.e. it's causing a change in magnetic flux. So when it cuts through that magnetic field lines, that's when like an EMF is induced or a current is induced. Well, you have to most often you have to mention EMF, but you can also get away with mentioning current. So when you rotate this, so let's say you're rotating it in this direction, okay, a current would be induced in this part and in this part. So if you recall the apparatus used for a DC motor, you'll realize a difference, like a few differences. And in IGCSE, they often ask the difference between the apparatus and the mechanism, the working mechanism of an AC generator and a DC motor. So the first difference that you can state is within the name itself, AC versus DC. So in an AC generator, an alternating current is induced. And in a DC generator, sorry, not a DC generator, a DC motor, a direct voltage is used. It's not, in DC, there is no inducing of current. You use the current to induce an kinetic energy. In AC, you induce the electrical energy, right? So it's obviously alternating current versus direct current, okay? That's like the first difference. Another difference is, if you remember the split ring commutator, in this it's not a split ring, but it's a slip ring. A slip ring commutator is used, okay? And it has two slip rings. Unlike the DC motor, which has one, it has two slip rings. Now the reason for this is not something that you really need to know. So just know that it has two instead of one. And well, that is pretty much it. Well, no, there's another difference, right? The other difference is that because in AC generators, you're not using current to induce like kinetic energy. There is no battery. Like there is no battery. There's no battery here. Like there's no battery, because an alternating current is being induced. So this is directly used to power something else. You don't normally they don't use a battery to store the power and then use that battery somewhere else. I don't think that's even practical. There's a lot of loss of energy. So they use this like to directly power something else. So let's say an AC generator can be used to power, let's say, a car or a machinery. Obviously, before you don't directly power it because okay, this is another thing that we'll have to get into. I wanted to get into it later, but we'll just get into it for the fluidity. So when an EMF is induced, okay, EMF induced, and this is over time, seconds. It doesn't even have to be in seconds, it can be minutes as well. But so when an EMF is induced in an AC generator, it goes like this. So when it's horizontal, when it moves from horizontal to like till this, it moves from horizontal to this position, right? There's a maximum EMF, okay? And when it's vertical, there's no EMF. So when it's vertical, you have to know these points. Vertical, no EMF, and when it's at horizontal, okay, let's just take that as an abbreviation for horizontal, maximum EMF is induced. Okay, so it goes like this. It goes like waves. Well, if you're in A levels, or if you have done a bit of graphs before, this is basically a sine graph. But this is how the EMF is induced, and the amplitude of the waves are equal. It may not look like it, but the amplitude of the waves are equal. So this is how the EMF is induced. Okay, and at this point it would be horizontal, and at this point where it's zero, EMF is zero, the 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 coil, the armature, would be vertical. This is very important. I'm not sure how much of this is in the syllabus, but I've seen it asked a few times before, so it's good that you know this graph and also these two things. Okay, and this brings me to my next point, or actually not my next point. It connects to my previous point where I was saying that you directly power things. You see that when you try to directly power things from an AC generator, right, there's a period of negative voltage, or the voltage is not consistent. Like it goes up and then goes down, increases, decreases to zero, and it fluctuates around zero. Okay, so you don't ever directly power something using an AC generator. You actually have other things in between, such as capacitors and transistors and other complicated circuits, but that is beyond the scope of your syllabus. All you need to know now is the working principles of an AC generator. And I think that is it for electromagnetic induction. There's another part, but that I'll be covering in another video because it also has its own, like the mechanisms are the same, but it has two different formulas and like a different working mechanism. And that is transformers, and we'll be covering it another day. I hope you understood. If you do have any doubts, please do leave them in the comment section below.